Hey everybody, welcome to our AP Stats review series. In this video, we're going to dive into Unit 1, exploring one variable data. Now, whether you're just starting or cramming for the exam, this is everything you need to know fast and focused. Overall, the AP Stats exam is 3 hours, 40 multiple choice questions, that's half the exam, your 6 free response questions, 50% of the exam. You're allowed to use a calculator on the whole exam, and you also have a formula sheet and tables. 15 to 23% of the questions will fall under the topic of exploring one variable data from Unit 1. First, let's break down some basic terms. Individuals are the objects described by a data set, like people or animals. Variables are characteristics we measure, and they come in two types, categorical and quantitative. Categorical variables, these place individuals into categories like gender or eye color, while quantitative variables, they are numerical values typically representing a measurement like height or weight. The distribution of a variable tells us what values it takes and how often it takes them. Here's a couple examples of bar graphs and pie charts. So in a bar graph, we're going to represent category frequencies with bars, while in a pie chart, we show category proportions as a slice of a circle. With a histogram, we group its values into intervals to show the distribution. With stem plots or stem and leaf plots, we display the distribution, shape, and individual values. When we display quantitative data, we sometimes use a time plot. This shows each data value plotted against the time it was measured, and the time scale should be on the horizontal axis and the variable of interest on the vertical axis. Connecting the points with lines helps to reveal the overall pattern or trend over time, especially when there aren't too many data points. A key skill is recognizing the shape of a distribution. There's symmetric, where the right and left sides are essentially mirror images of one another. There's skewed to the right or positively skewed. This is where the tail extends to the right. And skewed left or negatively skewed. This is where the tail extends to the left. One of the key features is to be able to identify outliers. An outlier in any graph of data is an individual observation that falls well outside of the overall pattern of the graph. To calculate, you just take the Q1 value and subtract 1.5 times the IQR, and anything below that is going to be a lower outlier. And for the upper outliers, anything above Q3 plus 1.5 times the IQR. Now, when we measure center, there are several different ways to do it depending on the kind of data that we have. The mean is the average of all data values. You just add those up and divide by how many. The median is the midpoint of a distribution. That is, half the observations are going to be smaller and half of them are going to be larger. It's important, though, that when you calculate the median, you have the data values in numerical order from least to greatest. If you have arranged those and you have an odd number of data values, then the median is at the center position. If you have an even number of data values, there is no middle value. So you go to the middle of the data set and take the average of the two middle values at those positions. Another key characteristic is the 5-number summary and box plots. The 5-number summary includes the minimum, Q1, the median, Q3, and the maximum. You can see in this computer output here, I've highlighted the 5-number summary, and oftentimes in computer outputs, they will give you the 5-number summary. Now, a box plot Q1 to Q3 to make the box. The line marks are going to be Q1 and Q3, with the median being in between those two values. The whiskers extend to the max and min value, and if you have outliers, they will be typically indicated with a dot or an asterisk outside of those whiskers. Now, when we talk about measuring spread, there are a couple ideas that we need to make sure we understand. The range is just how far apart the max and min values are, so you just subtract those two values. The interquartile range is Q3 minus Q1. Q1 is the 25% mark, and Q3 is the 75% mark of the data values. Now, when we measure standard deviation, a quick walkthrough of calculating standard deviation. Remember, it's the square root of the average of squared deviations from the mean. It basically tells us how spread out our data is. If we have data values of 6, 3, 8, 5, and 2, you would add those up and divide by how many? You get 4.8. Then you subtract each of those values by 4.8. So 6 minus 4.8 is 1.2, and so forth and so on. Then you square each of those values, add them up. We would have 22.8, and divide by 1 less than the number of data values. So 22.8 divided by 4. Take the square root of that, and you'd have 2.387. Now, when we choose a measure of center and spread, typically mean and standard deviation go together, and median and interquartile range go together. If your data is symmetric, then you're going to want to use the mean and standard deviation. If your data is skewed to the left or skewed to the right, then you're going to use the median and interquartile range. Now, when we talk about describing a location in a distribution, a density curve is an important thing to understand. It always is on or above the horizontal axis and has an area of exactly 1. It represents the overall pattern of a distribution, and the area under the curve within an interval equals the proportion of observations in that interval. If you look at the density curves in the image here, the image on the left is a density curve. It goes from 0 to 4 and has a height of 0.25. So if you multiply the base times the height, you get an area of 1. The figure on the right represents the proportion of data between 2 and 3. The width of that interval from 2 to 3, if you just subtract 2 from 3, you get 1 unit wide. The height of that density curve is 0.25, so 1 times 0.25 gives us a proportion of 0.25. Now, when we're thinking about a density curve, the median is the equal areas point. It divides the area under the curve in half. The mean, however, is the balance point. That's where the curve would balance itself if it was solid and you balanced it right on that point. In a symmetric curve, the mean equals the median. However, in a skewed curve, the mean is pulled in the direction of the tail. So if you're skewed to the right, the mean is pulled to the right of the median, and the mean would be greater than the median, and vice versa if the data was skewed to the right. Now, one of the most important distributions, we're going to look at a normal distribution. This is a bell-shaped curve that is symmetric and represents a continuous variable, and it follows what we call the 68, 95, 99.7 rule, which means that 68% of the data fall within 1 standard deviation, 95 within 2, and 99.7 within 3 standard deviations. Now, when we talk about the normal distribution, often standardizing and z-scores will come up. The z-scores measures how many standard deviations an observation is from the mean. It can be positive or negative, depending if that observation was above or below the mean. You just take the difference between the observation and the mean and divide it by the standard deviation. And this is useful for comparing values from different distributions. The standard normal distribution has a mean of 0 and a standard deviation of 1 unit. And any normal distribution can be standardized using the z-score formula. Oftentimes, you'll be able to use a standard normal table. This is also included in the formula sheet on the AP Stats exam. Here I have a screenshot of it, and it always is going to show the area to the left of a z-score. So if you're asked for the proportion of values to the left of a specific z-score, the area is just equal to whatever the table value is for that z-score. If you're asked for the area to the right, you find that table value for the z-score and you subtract it from 1, because the table always gives you the area to the left. You know the area under the entire density curve is 1, so you subtract that. Now, if you're asked for the area between two certain z-scores, you take the difference between those two entries for z1 and z-score number 2. Sometimes you're asked to kind of work backwards and you have to do an inverse normal calculation. Basically, you start with the given area and work backwards to find the z-score. So all we do is solve the z-score formula for x, which indicates the observation value. So x is the mean plus the z-score times the standard deviation, and that will help you find the original data value. Now that wraps up our overview of Unit 1, exploring one variable variable data. Make sure you review these concepts often as they're foundational for the rest of the course and they show up in every AP exam. Now what I want to do is jump into some practice problems with you guys. The first section, we're going to look at some multiple choice questions, and then we will go through a couple free response questions as well. So up first here, you measure the age, marital status, and earned income of a simple random sample of 1,463 women. The number and type of variables you have measured is, notice here we are measuring age, marital status, and earned income. Those are the three variables involved. So A, B, and C are eliminated. Two of those are quantitative and one is categorical. So their age would be quantitative and their earned income would be quantitative. Their marital status is a category, so that would be choice E here. Next up, normal body temperature varies by time of day. A series of readings was taken of the body temperature of a subject. The mean reading was found to be 36.5 degrees with a standard deviation of 0.3 degrees. Recall that F equals Celsius times 1.8 plus 32. When converted to F, the mean and standard deviation are, well, here's the thing. The mean is affected by multiplying and dividing and adding and subtracting. So if the mean was 36.5, to convert it to Celsius, we'd have to multiply it by 1.8 and then add 32, and we get 97.7. All the answers have 97.7, so that doesn't really help us out. However, the standard deviation is only affected by multiplying or dividing by a constant. So the standard deviation of 0.3, we would multiply that by 1.8, and you get 0.54. Okay, so it's choice C there. The reason for this is that the standard deviation measures how spread out the data is. So if you add 32 to all the data values, that's only going to shift the graph up or shift it down if you're subtracting values. So that's not going to affect how spread out it is. It's only when you multiply or divide. Next up, the weights of the male and female students in a class are summarized in the following box plots. Which of the following is not correct? So if we read through each of these, about 50% of the male students have weights between 150 and 185. So 150 is right about here. 185 is right about here. Those are the boxes. That's the 50%. So that's true. So that's not the one we want to pick. About 25% of female students have weights more than 130. So 130 is right about here. This whisker represents 25%, so this is correct. C, the median weight of male students is about 162 pounds. The median is the line in the middle of the box plots. That's at about 162, so that is also correct, not the one we want. And the mean weight of female students is about 120 pounds because of symmetry. This also is true or correct because if you look at the female box and whisker plot, it's roughly symmetric, so the mean and median are going to be very, very close. So that only leaves E as our choice. The male students have less variability than the female students. Well, that's not correct because you could see that the box plot is way more spread out than that of the females. Next up, we have a medical researcher collects health data on many women in each of several countries. One of the variables measured for each woman in the study is her weight in pounds. The following list gives the 5-number summary for the weights of women in one of the countries. About what percent of country A women weigh between 110 and 200 pounds? So if you remember, the 5-number summary gives the min, Q1, the median, Q3, and the max. Now, between each of these is 25% of the data. So if we go from 110 to 200, that's going to be the 75% of the data. So that's choice C. Next, a sample of 99 distances has a mean of 24 feet and a median of 24.5 feet. Unfortunately, it's just been discovered that an observation which was erroneously recorded as 30 actually had a value of 35. If we make this correction to the data, then, well, here's the thing. If we have the same number of data values and one of the data values was changed from 30 to 35. Both of these values are above the mean. This is going to affect the mean, not the median, because the median's the middle value, and if one of the values above the middle is changed, it's not going to affect which value was in the middle. However, since the value above the middle is increased, it's going to affect the mean, and it's going to pull the mean a little bit higher. So that's going to be choice C. The median remains the same, but the mean is increased. Now, the heights of American men aged 18 to 24 approximately normally distributed with a mean 68 inches, standard deviation 2.5 inches. Only about 5% of young men have heights outside the range. So with a mean of 68 and a standard deviation of 2.5. So if we're normally distributed right here, we have 5% outside of the range. That means we're looking at the middle 95%. That would be two standard deviations above and below the mean. So 68 plus 2 times 2.5 and 68 minus 2 times 2.5. And that's going to give us a range of 63 to 73, which is choice B. For the density curve shown below, which statement is true? The mean and median are equal. That's not going to be true. This curve is skewed to the left. So we know that the mean and mean are not going to be equal because that's only true if it's a symmetric distribution. The mean is greater than the median. That's not true. If the mean is greater than the median, that would result from being skewed to the right. So this one, the mean is less than the median because the graph is skewed to the left. Suppose that 16-ounce bags of chocolate chip cookies are produced with an actual mean weight of 16.1 ounces and a standard deviation of 0.1 ounce. The percentage of bags that will contain between 16 and 16.1 ounces is, so if the mean is 16.1 and the standard deviation is 0.01 or 0.1, then you would go one standard deviation below the mean. On a standard normal curve, one standard deviation is 68%, but that's above and below. We're only going half of that, so that would be 34%. So 34% is between those two values. For the density curve shown here, what percent of observations lie between 0.5 and 1.2? So if this is a density curve and it goes from 0 to 2, that means that the height has to be 0.5 right here. So if I go from 0.5 to 1.2 right here, if I subtract those, I get the width of that interval, which is 0.7. And then I have to multiply the width of that interval times the height to get the area. So 0.7 times 0.5, or half of 0.7, is 0.35. So 35%. Suppose the distribution of math SAT scores from your state this year is normally distributed with mean 480 and standard deviation 100 for males and mean 440 and standard deviation 120 for females. If someone who scores 780 or higher on a math SAT can be considered a genius, what is the proportion of geniuses among male SAT takers? Now here, there's some extra information we don't need about the females because the question only asks among male SAT takers. We can use the calculator and you would do normal CDF with the lower being 780, the upper, just pick a larger number like 1,000. That's fine. The mean is 480 and the standard deviation is 100. If you calculate that, 0.0013, which converts to 0.13%. So that wraps up our example questions for multiple choice. Let's look at a couple free response questions here. The test grades for a certain class were entered into a mini-tab worksheet, and then descriptive statistics were requested. Here's the results. Determine the IQR for this data. So for part A, the IQR is Q3 minus Q1, which is 84 minus 68, which gives us 16. Using the answer from part A, determine whether the lowest and highest values in the data are outliers. So to get an upper outlier, you would have to take Q3 plus 1.5 times the IQR. So Q3 is 84 plus 16 times 1.5 is 24, which gives you 108. Since the max is 94, the max is not an outlier. For the lower outliers, you would have to do Q1 minus 1.5 IQRs. So that would be 68 minus 24, which is 44. The minimum of 35, 35 is below the boundary for a lower outlier. So 35 is a lower outlier. Following data represent the scores of 50 students on a calculus test. There we have it. We want to construct a frequency histogram for this data set. If this is a free response question, don't waste your time trying to calculate this by hand. You're allowed to put this data into your calculator, calculate the histogram, and then copy it down. Here we go. We would just put all the data value into a list in your calculator, then hit zoom stat, and you might want to change the bin width to be about 5 just to even it out a little bit. And then you would copy this down, but make sure that you label the graph. Like the bins here go from 40 to 50 to 60 all the way up to 100, and the height all the way up to 15. And this would be test scores, and this would be number of students. Now, if we have to describe the shape, center, and spread of the distribution of test scores, the shape is roughly symmetric. The center is approximately 73, and the spread is from 49 to 99. And you could just get that from the lowest value to the highest value in the data set. Next one, during the early part of '94 baseball season, many sports fans and baseball players noticed that the number of home runs being hit seemed to be unusually large. Here are the data on the number of home runs hit by the American and National League teams. Want to construct a back-to-back stem plot and compare the number of home runs hit in the two leagues. You can't do this on the calculator, but the data values are in order, so this makes it a lot easier. Remember, your stems go down the middle. We're going to use the tens. So we start at 20, 30, 40, 50, 60, and 70. We don't need any others because the data values fall outside of that range. So for the American League, there are no 20s. They start at 35, and then you have 40, 43, 49, 51, 54, 57, two 58s, 64, 68, 68, 75, and 77. For the National League, you have a 29, 31, 42, 46, 47, two 48s, 53, three 55s, 63 two times, and a 67. Now we want to write a few sentences comparing the distributions of the two leagues. Be sure to include a comparison of the medians as a part of your discussion. Now, overall, the American League team hit more home runs than the National League. You can see that easily from the data values in 1994. Also, the median for the American League was 57.5. 57.5. Because the two middle values, if you count up, so since there's 14, you would count up 1, 2, 3, 4, 5, 6, 7. Get these two middle values, 58 plus 57 divided by 2 gives us 57.5. And the National League median, get those two values, 48 plus 53 divided by 2. That's going to give us 50.5. Also, the low value for the National League is much lower than the low value for the American League. So it's like 29 versus 35. Also, similar thing with the high values. The American League at 77 is much higher than the National League at 67. Here we have a density curve below that is uniform. It goes from 0 to 2 on the x-axis and 0 to 0.5 on the y-axis. Verify that the area below the density curve is 1. All you got to do is multiply base times height. So 2 times 0.5 equals 1. So we're good there. What proportion of observations are less than 0.75? So 0.75 is roughly here. Okay, you don't have to draw it, but I just like to shade it to see it. So 0.75 is the base. The height is 0.5. So that would be 37.5% or 0.375. What proportion of observations are greater than 1.5? So 1.5 is right about here. What you have to do is take the width of this interval, which is a half, but you could get it by just subtracting 2 minus 1.5, which is 0.5. Then 0.5 times the height of 0.5 gives us this area right here of 0.25 or 25%. Next question, in a study of elite distance runners, the mean weight was reported to be 63.1 kilograms with a standard deviation of 4.8 kilograms. Assume that the distribution of weights is normal. Sketch the density curve of the weight distribution with horizontal axis marked in kilograms. Here we have the kilograms, the mean 63.1. We're going to add the standard deviation each time. If we add 4.8 to that, you would have 67.9. Add it again, 72.2. Add it again, you'd have 77.5. Take 63.1 and we want to subtract the standard deviation 3 times. So subtract it once, 58.3. Subtract it again, 53.5. And subtract it again, 48.7. The peak is going to be above the median right here, and it's going to have that bell-shaped curve to it. Okay, so that's part A. What range represents the middle 68%? So the middle 68% is one standard deviation. So that would be 58.3 to 67.9. What percentage of runners' weights are less than 58.3? 58.3 is right here, so we want the percentage that is down here. Now, if you remember symmetry, from the median down is 50%. One standard deviation above and below is 68%, so that means that 34% is one standard deviation below. So if I do 50 minus that 34%, I would get 16%. What percentage of runners' weights are between 63.1 and 72.7? So 63.1 and 72.7. That would be this amount right here. If we remember that this is going to be 34%, there's one standard deviation above. The next is 95%. So half of that, so if we go 2 standard deviations, that's going to be 95%. And half of that would be 2 standard deviations above only, which is 47.5%. So that's going to be our answer for D, 47.5%. Now, our last question here, a lunch stand in the business district has a median daily gross income of $520 with a standard deviation of 50. Assume the daily gross income is normally distributed. In what proportion of days is the gross income less than 400? So for this, we could use the calculator. We're going to click on normal CDF, and we're going to put the lower as negative 1,000, the upper as 400, mean and standard deviation entered in there, and you get 0.00819. If you have to write this, you would write normal CDF. If you have to write this on a free response question, you would have to write lower, negative 1,000, upper, 400, mean, 520, standard deviation, 50. And then you could write equals 0.0082 if you rounded that. Next one, in what proportion of days is the gross income more than 600? Here, 600 is the lower, and then the upper would be 1,000. Mean and standard deviation are still the same. You have 0.054. 0.48 if you round. Next one, what proportion of days is the gross income between 400 and 600? Here, the lower is 400, the upper is 600, and you'd have 0.937. And the last one, what does the gross income need to be for a day to be in the top 10% of all days? So here, essentially, they're giving you the area and asking you for the observation value. You would want to use inverse norm. The 0.1 is the area. The 520/50 is mean standard deviation, and the right is which tail you're going for. Since it's the upper 10%, we're going to do the right. So again, with this one, you're going to have to label each of those numbers. All right, guys, that wraps up Unit 1. Make sure you give this video a like, comment below with any questions you have. Make sure you share it and subscribe for more updates. I'll always be releasing more stuff.